So, hello Year 12, welcome back, and I hope that you found the first part useful. We're going to continue going through the large topic 5, Formulae, Equations and Amounts of Substance, part 2. Yes, part 2 of 2 hopefully, although next week I'll probably set you some questions without the video to go with those. So, we looked at this the other day. The fact that some of this stuff you would have known from GCSE, Avogadro constant in calculations, and writing balanced full and ionic equations. Do give me a shout if you want me to go through any more of that. This is the second half of the spec for the first topic 5 that we did, and you can see that there's 2 core practicals, core practical 2 and core practical 3. You might remember these: preparing a standard solution and finding the concentration of a solution of hydrochloric acid. That was a titration. Again, there's stuff here from GCSE, so percentage yields and atom economies you should be familiar with. And you may also have looked at ionic equations of displacement reactions, acid reactions and precipitation reactions. And hopefully after the last session you're okay with those. We've also got to look at minimizing errors. So we went into errors in a lot more detail this time, and we'll look at those, and understanding risks and hazards in practical procedures and suggesting appropriate precautions. Again, trying to make these a little bit more grown up than GCSE, so thinking about what are the dangers rather than default stuff. So going to titrations, a chemist makes 500 centimeters cubed of a solution of nitric acid of concentration 0.8 mole per dm cubed. What mass of nitric acid or hydrogen nitrate does he need? Well, of course, the first equation we've got is that the number of moles, N, is concentration times volume. We've got the volume in centimeters cubed, but don't forget we must put the volume into decimeters cubed. Otherwise we won't get the right number of moles, and concentration is 0.8 mole per dm cubed, and therefore the number of moles is 0.4 moles. Okay, part 1 of a 2-part question this, because now we need the mass. Nice and easy. We can work out the mass we need from the number of moles times the relative formula mass, one of your mole equations from GCSE. So 0.4 moles times 63 grams per mole gives you 25.2 grams. And being able to do these 2 steps quite quickly is important. It'll often be only worth 1 mark at A level. Second question, a similar idea. A student has 50 grams of sodium chloride. What volume of a 0.45 mole per dm cubed solution can she make? Okay, so we know the mass of sodium chloride, we know the concentration that we want. The first thing we've got to do is we need to convert the mass into a certain number of moles. So number of moles, mass over molar mass. So we've got 0.855 moles of sodium chloride there. And the second thing is we know the concentration we want, we know the number of moles we've got, so we can rearrange the equation. The volume we can make is the number of moles over the concentration, 0.855 divided by 0.450. We can make 1.9 decimeters cubed, just under 2 litres. And being familiar with converting between concentrations and volumes and masses, it's often tacked on there at some point, 1 or 2 marks in a larger titration question. So what is a titration? Well, very simply, what we're trying to do is we are trying to work out the concentration of an unknown solution by comparing it to a known solution where we know the concentration accurately, and by the reaction we can work out the concentration of the unknown solution. So it's sometimes known as volumetric analysis. And CPAC 2 was all about making standard solutions. So standard solution is a solution whose concentration is very accurately known. So this is the key thing. We must absolutely know the concentration of that standard solution, because the more accurately we know the concentration of the standard solution, the more accurately we can know the concentration of the solution that we're trying to find out. We call them primary standards, so the ones that we know very accurately. And this is just a note that we use a lot of sodium hydroxide and hydrochloric acid in school as our standard solutions in our acid-based titrations, but for various reasons that maybe you could have a think about, and just say it down there, they're not actually very good solutions to use for titration. This is using a standard solution to perform a titration. You should be very familiar with this method from GCSE, but also at A-level you had to do it a little bit more carefully. Some things I want to note is up here it says rinse the conical flask with deionized distilled water, but you rinse the pipette with the solution that you are going to use. So you're going to rinse the pipette with some sodium hydroxide. You're also going to rinse the burette with the solution you're going to use. So pause the video and think, why do we not rinse the conical flask with the solution that's going to go in it, but we are going to rinse the pipette and the burette with the solutions that are going to go in it? Okay. Well, hopefully you realised that the really crucial thing in the conical flask is that we know exactly the number of moles that are put in. So if we rinse the conical flask with the solution that we're going to use, and there's a few drops of that solution in the conical flask, that is going to affect the number of moles of the solution that's in there, and it's going to affect our calculations and the titers that we get. However, we need the burette and the pipette to be rinsed out properly, because actually any drips that are in there just get taken into account because we're measuring them. So if there's a few drips left in the burette when we fill it up with the correct solution, well, so what? The drips are going to get absorbed into the volume, and we're going to actually measure the volume that we use. The pipette, the same idea. If there's a few drips of the solution left in the pipette, well, we measure up to the line, so it doesn't matter. And actually what matters more with the pipette and the burette is that they've got a solution that hasn't been watered down, hasn't been diluted by any drips of the deionized water, and that's why we rinse those with the solutions after the deionized water. We add the acid to the alkali solution till the indicator just changes colour. We record the burette reading, and we look at the coarse titer, the rough titer. In terms of concordant results, here it says within 0.2 centimetres cubed. Often you're told 0.1 centimetres cubed. You'll almost certainly be told in the question otherwise. Go with 0.1 centimetres cubed. You do need to know certainly these two indicators, ideally litmus as well. You should be familiar with this one from Key Stage 2. Litmus indicator, blue in alkaline solution, red in acid solution, and purple at exactly neutral. Methyl orange, well, it's orange, so you know the two colours that are going to make it up, red and yellow. Just like litmus, it's red in acid and it's yellow in alkali. Sometimes we focus on the fact that it's sort of an orange colour at the exact point of titration, and the mark schemes I've seen have always allowed the end point is orange, so you're allowed to do that. Phenolphthalein, okay, it goes from pink to colourless, okay, not clear, colourless. Make sure that you are familiar with that. Make sure that you know where the change is occurring in what direction, because if you get them the wrong way round, or if you're not specific, you will not get the marks for those. Hopefully we hammered into you during the required practical that we really did need to record the titers to 2 decimal places, where the second decimal place is a 0 or a 5, and we'll come back to that idea with error analysis in a bit. But let's say you started off at 0.55 and your final burette reading was 21.35, okay, recording that end number. and you want to know what the difference is, well, subtracting the two of those, you obviously get 20.80. Do record the average titer to the right number of significant figures. If you don't do that, if you just wrote 20.8, then you will not get the marks for that. So all burette readings need to be to the half of the smallest division there. To make the standard solutions, this was core practical 2, you obviously had to measure up to the line on the volumetric flask. Quite important that you realise we always read so that the bottom of the meniscus is on the line, and you should also always look from eye level, so you make sure your eye is at the level of the bottom of the meniscus when you read. You do not look from above or below, because then you might think, oh yeah, that's actually on the line. It's not, you're just not looking from eye level. Okay, so do make sure that you do that. Primary standards. So the standard solutions you will use in your titrations is a solution whose concentration is very accurately known. We need to ideally take a known mass of a substance and dissolve it in water. This is the problem with hydrochloric acid, okay? It's not a solid. And actually dissolving a mass of a gas is not very easy to do. So we want a solid. They've got to have high molar masses, okay? And we need the high molar masses to minimize weighing errors. So minimize weighing errors. So the smaller the molar mass, the less you need to weigh out and the bigger the error in weighing. High degree of purity, of course, need to be chemically stable, not decompose or react with substances in the air, not absorb water from the atmosphere. And this is, of course, the problem with sodium hydroxide, is that it does both. It absorbs substances from the water from the atmosphere and reacts with it. And that's why that's a really poor primary standard. As a solid, it's hygroscopic, it absorbs water from the atmosphere. Then when you make it up, it reacts, the hydroxide reacts with carbon dioxide to form carbonates, and that's why there's a lot of scum in hydroxide solutions that have been left around. Obviously needs to be soluble in water and needs to react rapidly and completely. So do make sure you know this, these ideas, because you might be asked to give a couple of examples of what would be a good primary standard. And there you go, hydrochloric acid and sodium hydroxide. This was your method for required practical 2. Add between 2.3 and 2.5 grams of sulfuric acid to the weighing bottle. Weigh accurately. Transfer as much as possible of the acid to a clean beaker. Reweigh the weighing bottle. The idea of weighing by difference there. Add about 100 centimeters cubed of deionized water to the beaker and stir until all the sulfuric acid has dissolved. And remove the stirring rod, washing traces of solution from the rod into the beaker using the wash bottle. So the idea of adding the washings there. Funneling the neck of the volumetric flask, pour the solution in, rinse the inside of the beaker several times with the wash bottle and transfer the rinsings into the flask. Make sure you do that. Make up exactly to the graduation mark. Stop at the flask and invert several times to make a uniform solution. We had the year before, some people forgot to do that, and as they went through their titrations in CPAC 3, they noticed that the titers kept drifting because the stuff in the neck of the bottle was less concentrated than the stuff in the rest of the flask. So it is important you do that inversion. Here's a question from an exam paper. Read the following instructions to describe the standard solution. Take a clean 250 centimeter cube volumetric flask, use the balance and a clean dry container to weigh out the amount of solid required, tip the solid into a clean dry 250 centimeter cube beaker, add 100 centimeter cube distilled water, help the solid dissolve, breaking up any lumps. When the solid is dissolved, pour the solution into the flask using a filter, add the water to the flask until the level rises to the graduation mark. Suggests 3 further instructions that would improve the technique. Well, the first thing is the idea that we want to weigh by difference. So tip the solid into a clean beaker, reweigh the container. So that would be the first thing, so that we weigh by difference. Use a stirring rod, help the solid dissolve, carefully break up any lumps of solid with a wash. With the rod, when the solid is dissolved, pour the solution to the flask using a filter funnel. And then the idea of adding the washings would be an obvious one. So rinse out the stuff from the beaker through the funnel many times. Fill it to the graduation mark and then invert to mix. So these are the three that instantly stand out to me that would allow you to make a much better solution. With the titration, we've got this method here. We've talked about all of this. Obviously, one of the reasons you might be asked, why not add loads of indicator? Well, it's a compromise, because if you don't add enough, then your endpoint's not going to be very obvious. But some of these indicators are actually weakly acidic, and so if you add too much of them, they will affect your reading. So do be aware of that. When conducting the titration, remember to wash down the inside of the conical flask with distilled water. That's just to try and make sure that if there's any drips of stuff from the burette down the sides of the flask, they get washed in to the solution at the bottom. Why do we do this? Well, we make sure that all of the solution that's come out of the burette goes into the conical flask. Why doesn't it affect the accuracy of your final result? Well, the crucial thing is just the number of moles of the stuff that's in there. We don't really care about the concentration. We're just doing a mole to mole comparison when we do a titration. So suggest a reason for removing the funnel after it's been used for filling the burette. Stop the drips. So if something drips in from the funnel during the experiment, it's going to ruin the result. Suggest one other source of error in using the burette to carry out the titration. Well, an obvious one, and the one that they're interested in here, is if there's sort of an air bubble in the jet of the burette. No, sorry, that's a terrible drawing. That's my tap. If there's an air bubble that is dislodged during the practical, then that again is going to affect your results. Why does rinsing improve the accuracy of the titer? That's what we've just talked about. It ensures that all solution from burette is in flask. So this is talking about rinsing it during the titration, not before, okay? So during the titration, explain why adding this extra water does not change the volume of EDTA solution that is required in the titration. That's because the number of moles in flask is conserved. Diluting it down does not affect the number of moles in that flask. Right, another thing that people struggle with, parts per million calculations. And if you understand percent, you understand parts per million. So, an average UK adult male has a mass of 80 kilograms. They have about 4 grams of iron in their body. What is this as a percent? Well, okay, 4 grams over 80,000 grams gives us the fraction of the body, that is 0.00005. So if we want to know how many parts there would be in 100, it's 0.05%. And I doubt any of you would struggle with that. Percent means per 100. Parts per million, parts per 100. See the link. We first find out the fraction, then multiply by 100 to find out how many bits in 100 in the body would be iron, and it's 0.05. For parts per million, we do the same thing. An average UK adult male has a mass of 80 kilograms, 4 grams. What's the amount of iron in the body in parts per million? So 4 divided by 80,000, the same fraction here. Now we just want to know how many parts in a million are going to be iron. Times that by a million and we get 50. ppm means parts per million. We find the fraction, multiply by a million, okay? So just look at the comparison. When we're comparing percent to per million, we find the fraction in both cases, And in one of them we times by 100 to find out the fraction, the number in 100 that would be iron. And for parts per million, we just multiply by 1,000,000 to find out the number in 1,000,000 that would be iron. So clearly converting between the two is very, very straightforward. To move from percent to parts per million, we divide by 100 to find the fraction and then multiply by 1,000,000. And to go the other way, so to go from parts per million to percent, we divide by 1,000,000 to find the fraction, and then we times by 100 to find the number that there would be in 100. So actually it's very straightforward. If you just understand, we find the fraction and then we multiply by 100 to find the fraction in the number in 100, or we multiply by 1,000,000 to find the number in 1,000,000. There was a small bit, this is covered elsewhere, but combustion analysis. So when you burn a carbon fuel completely, all of the carbon in your fuel ends up as carbon dioxide. All of the hydrogen in your fuel ends up as water. And therefore, if you know the number of moles of this, you can find the number of atoms of carbon in your fuel. If you know the number of moles of this, you can find the number of moles of hydrogen in your fuel. So let's have a look at that. An alcohol combusts completely, releasing 17.6 grams of carbon dioxide, 9 grams of water. What's the mass of carbon and hydrogen in alcohol? So we got 0.4 moles of CO2. So that means we got 0.4 moles of carbon atoms in the fuel. Each carbon atom gives one CO2 molecule. So a mole of carbon atoms gives a mole of carbon dioxide. And we can work out the mass of the carbon in the fuel, because if we've got 0.4 moles of carbon atoms times 12, 4.8 grams. We've got 0.5 moles of water. So we can say, well, I know that each water molecule has got 2 hydrogens, H2O. So if I know that I've got 0.5 moles of water, I've got 1 mole of hydrogen. Because every 2 hydrogen atoms gives 1 water molecule. So every 2 moles of hydrogen atoms in the fuel will give 1 mole of water. So again, if I know the number of moles of hydrogen atoms, I can work out the mass of hydrogen in the fuel. You'll notice that there's some oxygen in the fuel because it's an alcohol. So in order to work out the exact formula of this, we do need a little bit more information. So we have a problem in that the oxygen, some of it comes from the air, some of it comes from the fuel. So we can't say directly how much oxygen comes from the fuel. But if we are told that 7.4 grams of an alcohol combusts completely, releasing this amount of CO2 and water, now we've worked out the amount of carbon, we've worked out the amount of hydrogen. So we can actually say the mass of oxygen that must be in that fuel. 1.6 grams must be oxygen from the fuel. So therefore, we can work out the ratio of the number of moles. So we know that there's 0.4 moles of carbon, 1 mole of hydrogen, 0.1 moles of oxygen. And we need to put this into a ratio. Simplest thing, divide by the smallest number. And we can see that the ratio is 1 to 10 to 4. In other words, C4H10O. Here's another example. 0.5438 grams of a sample of compound contains only carbon, hydrogen, oxygen, burned completely. The products are that amount of CO2 and that amount of water. First, number of moles of carbon dioxide, and that gives you the number of moles of atoms of carbon in the fuel. Number of moles of water, times that by 2, and that tells you the number of moles of hydrogen in the fuel. So let's have a look. We've got this number of moles of carbon dioxide, and so we've got that number of moles of carbon atoms. We've got this number of moles of water, we need to times it by 2, and that's the number of moles of hydrogen atoms. Next thing, what mass of carbon is that? What mass of hydrogen is that? Cool, so we know the mass of C and H. We're told the total mass of the compound up there, so any difference must be due to the oxygen. So 5438 minus those two numbers says that is the mass of oxygen. And we can divide that by 16 to get the number of moles of oxygen. So we know the moles of carbon, moles of hydrogen, moles of oxygen. They're not friendly numbers. What do? We'll divide by the smallest. Divide by the smallest number, and now we can get a ratio that looks far more friendly. We can see that the ratio is pretty much 2 carbons to 6 hydrogens to 1 oxygen, C2H6O. And if you want, here's some more examples. Pause this and have a look at these questions. But we shall continue. Back titrations. A question might say 1.25 grams of limestone dissolved or reacted with 50 centimeters cubed of hydrochloric acid at 1 molar. The resulting solution is made up to 250 centimeters cubed with water. We take 25 centimeters cubed for titration. We do the titration, and that requires 30 centimeters cubed of 0.1 molar sodium hydroxide to neutralize. The thing to remember with one of these back titration questions, which could be 7 or 8 marks, just start at the end. Start with the titration. That's the bit that's most familiar to you. Okay, 30 centimetres of 0.1 molar sodium hydroxide. Well, we know that is 0.003 moles. We know that the reaction between that and the hydrochloric acid is 1:1. So we know the number of moles of hydrochloric acid that are there at the start in that conical flask. Here, we took 10% of the whole volume, and therefore the number of moles of hydrochloric acid in that flask are 0.03. We started off with 0.05 moles of hydrochloric acid there, so the number that we used reacting with the limestone, the number that we used up is 0.05 minus 0.03. In other words, we used up 0.02 moles. From the reaction between limestone, which is calcium carbonate, and hydrochloric acid, we know it's a 1:2 ratio, so that number of moles of acid reacted with that number of moles of calcium carbonate. Calcium carbonate has the formula mass 100 grams per mole, so that is 1 gram of calcium carbonate in the limestone. And finally, therefore, we can say if 1 gram of it was actually calcium carbonate, the limestone was 80% pure. Here's another example. I'll run through the question and then you can pause the video and see if you can work it out. We've got 6.6 grams of fertilizer that we react with excess hydroxide generating ammonia solution. This is then bubbled through 50 centimeters cubed of hydrochloric acid at 1 molar. Of course, you'll need to know that the reaction between ammonia, NH3, and hydrochloric acid just gives you ammonium chloride, 1:1 ratio. That is made up to 250 centimeters cubed with water, titration, 20 centimeters cubed of 0.1 molar sodium hydroxide. Okay, so I want you to work back and see if you can work out the number of moles of ammonia that were made. Right, 20 centimeters cubed of 0.1 molar sodium hydroxide, 0.02 moles, reacts 1:1 with hydrochloric acid, so 0.02 moles of HCl in the conical flask down here. That's 10% of the whole, so we've got 0.02 moles of HCl in the whole flask. And because we started off with 0.05 moles of the acid, that means that we used 0.03 moles of acid. And that means that there must have been, you can't see it there, it's under my scribblings, but 0.03 moles of ammonia that were released here. You may then be asked to work out the purity of the fertilizer. So if the fertilizer was, for example, ammonium sulfate, and that gives 2 moles of ammonia, you can work out that there would be 0.015 moles of ammonium sulfate. So from here, you could, if you wanted, pause the video, work out the percentage purity. but that number of moles is 1.98 grams, so therefore the purity is 30%. Right, mistakes and errors. Mistakes are not errors. This is something that Key Stage 3 students can't get their heads around. Even GCSE students cannot tell the difference between an error in an experiment and a mistake that they made. A mistake is something that myself or Dr. Butterworth or Miss Watts or Mr. Barler can avoid by being careful. Things like forgetting to zero the balance, not writing your readings down correctly, not removing the funnels during titration. These are mistakes. But an error is something that we cannot fix. It's a problem inherent in the experiment, and no matter who does it, that is going to be a problem. So if you're in the lab, solutions might get hotter or colder. You cannot get rid of all the liquid on the inside of a pipette, no matter what you do. You can't get rid of impurities within or on the surface of reactants. These are just problems that you've got that you cannot fix. They're errors. You do need to know the difference between being precise and being accurate. And when I ask my students, no one gets the example correct. The example I always give is I am 2 meters tall versus I am 1.683 or 23 meters tall. Which one's precise? Which one's accurate? Well, this one is very precise. It tells you within a very small region what my height is, but it's wrong. I'm nowhere near that. This one is not very precise at all, but it's actually accurate. To the nearest meter, I am 2 meters. So that is correct. That is not. That is accurate, close to the true value. That is not accurate, but it is precise. So accuracy describes how close a value is to the correct or accepted value, whereas precision describes how close different values are to each other. In this case, it's only giving you a tiny amount of wiggle room between 1.68235 and 1.68225. So all the values that could contribute to that are very small. This is anywhere between 1.5 and 2.5. So there's a huge range in the numbers that could be, but it is right. Also, the difference between systematic errors. So systematic errors are where there's a problem with the experiment. So if you've got, for example, in a pipette, the end of your pipette has snapped off. So that means you're always going to measure too little of your solution in your pipette when you measure it out for a titration. You might get exactly the same titer every single time, but it's going to be wrong because actually the amount of liquid you've put in every time is wrong by the same amount. That's a systematic error. Random error, though, is changes in temperature, or if you're just being a little bit slapdash, so sometimes you undershoot, sometimes you overshoot, okay, in terms of the amount of liquid you add. That's a random error. And here we've got student A who has a high degree of precision but low accuracy. B actually is fairly accurate overall, but low precision, but you want to be there. Student C, precise and accurate. Random errors, unpredictable changes in conditions, varies about the true value, air currents, different amounts of impurity, burette changing volume. Systematic errors, these are apparatus always in the same direction, will always give you the same wrong. So thermometers with a gap in the liquid column, damaged balance, reading to the top and not the bottom of the meniscus, for example. Measurement uncertainty, nothing gives you an exact amount. So if we're weighing out 20 grams of calcium carbonate, the food tech balances, which might measure to the nearest gram, well, 20 grams is anywhere between 19.5 and 20.5. Our Key Stage 3 balances to 1 dp, they give you a higher degree of precision, but again, there's some variability. The ones you typically use, 2 dp, getting less and less availability in what the answer can be, but still there's a variation in what the true value could be, assuming that the balance is right. And then the ones that Mr. Reeves uses, the 3 dp balances or even the 4 dp, they are reducing the values it can be. The uncertainty gets smaller every time, but it is never zero. Question: a student could use a pipette or a burette to add 50 centimeters cubed of liquid to a conical flask. Using the table above, which is the better choice? Well, if we use the pipette, yeah, 25 centimeters cubed only has this source of error. But because we're using it twice, that means the overall error is 0.12 centimeters cubed. For the burette, however, each reading is 0.05 centimeters cubed, but we need to read it twice. So actually the overall error is 0.1. Still, for 50 centimeters cubed, the burette is better than the pipette. When you are trying to work out the uncertainty, some of them tell you what the uncertainty is, and things like volumetric flasks will have written on it the actual uncertainty. So they'll have a number like plus or minus 0.06 centimeters cubed. Other ones won't have the value measured on it, but you can work out the uncertainty by half the division. So here, for example, each division, 64, 68, 72, 76, 78, each one of those is 4 centimeters cubed. So the uncertainty of this is plus or minus 2 centimeters cubed, half the smallest division. So if we're reading this, we would read that as 62, because we're reading to the bottom of the meniscus, plus or minus 2 centimeters cubed. Be aware of that. Have a think if you want. Pause this. Think about what your errors are on each of these instruments. And here are the answers. If you're not sure about any of those, give me a shout, but half the smallest division. So for example here, this only measures to the nearest foot. Up here, this depth gauge, and therefore the reading is plus or minus 0.5 foot. This reads to the nearest 0.1 degrees C, so the uncertainty is half of that, plus or minus 0.05 degrees C. But the absolute uncertainty is actually not that useful. Uncertainty of 1 second is more significant for 10 seconds than for 100 seconds. We want to know how important it is as a fraction of the total. So we often work out the percentage uncertainty by dividing the absolute uncertainty by the measured value times by 100. And that's quite important, it's the measured value. So let's say you are using a balance and you measure out that the weigh boat is 1.32 grams, and then with your amount, with your stuff, it's 1.37 grams. Well, this is plus or minus 0.05 grams. This is plus or minus 0.05 grams. Sorry, 0.05, sorry, that should be 0.05 grams, half the smallest division, which is 0.01. So the total uncertainty is 0.01 grams in that answer. But what you actually measured is the difference there, which is 0.05 grams. So the uncertainty here is your absolute uncertainty, 0.01, over what you actually measured, 0.05, times by 100%, which is 20%. That's a huge amount. What students tend to do, unfortunately, is they might do 0.05 over 1.32 times 100%, and then 0.05 divided by 1.37 times by 100%, and then add those together. But that is completely wrong. That will give you a tiny percentage error, whereas actually it's huge. All right, so do be careful of that common mistake. Here we go, 3.57 grams marble chip weighed out. What's the percentage uncertainty? We know the reading each time, but the balance is read twice. So the percentage uncertainty, 0.28%. And you can work out the percentage uncertainty in the mass of the solid here. We've weighed the watch glass, we've weighed it at the end, and I'll let you work that out for yourself. Here's another example. Starting temperature is 15 degrees C on a thermometer, and final temperature 28 degrees C. Clearly reads to the nearest degree C. What's the uncertainty? I'm going to skip through this, but just saying pipette here, we can see the error written on it. So error over the amount you weigh out, 0.1%. And the burette here, okay, so we read a titer of 22.5 centimeters cubed. We might expect the error to be this, but of course it's not, because we needed to read 2 readings. And even if we started at 0.0, that is plus or minus 0.05 centimeters cubed, okay. There's an error at the start, and then 22.50 is also plus or minus 0.05, and therefore the total error is 0.1 over 22.5, which gives 0.44%. And so if we're working out the concentration from this, when we measured out the acid, the error was plus or minus 0.1%, the alkali plus or minus 0.44%. We add the two together to get the overall percentage error of the titration of the concentration. And if we've worked out from the titration what the concentration is, we know the accuracy of that in terms of percent. And if we are asked to, we can just convert that into the actual amount. It says down here, the volume of acid was known to 4 significant figures. However, the volume and the concentration of alkali were only known to 3 sig figs. Our final answer cannot be more precise than that. Be aware of that at the end. It does not make sense to ever give your answer to more significant figures than your least accurate piece of input data. You could be asked for other sources of error in a titration. Indicator may not change instantly. Colour change may not be obvious. They may not react instantly, the acid and alkali. Some acids, particularly weak acids, release protons fairly slowly. The tap may not steal instantly. You may have drips on the bottom of the burette which drip in. Alkali may have reacted with dissolved carbon dioxide, particularly true of sodium hydroxide. Acid left in the pipette. Hydroxide pellets may not be pure. These are the sorts of things you could talk about. Okay, so I hope you found that useful. We've gone through the rest of the spec there. I'm going to do the same as I did at the start of the week. I'm going to put a set of questions online. There's about 20 multiple choice questions. Then there's another 3 longer answer questions where I'm not giving you multiple choice. So work through at least the first 2 of those, questions 1 and question 2 of the non-multiple choice questions, and come up with an answer. Then have a go at the quiz on Show My Homework, and it'll hopefully self-mark. By Monday next week, hopefully you will have all completed the first quiz from earlier this week, and therefore I will go through the most wrong questions as a short video there, looking at the ones where the majority of people got them wrong. Don't forget, we are tracking the people that do this. It's very obvious who hasn't done the quizzes, and we are unfortunately forwarding the names of transgressors to Mr. Young. So do make sure you are doing the work. Other than that, I hope you're all getting on well. The lovely sunny weather out there probably means you're not wanting to be inside doing chemistry, but here we go. See you next week. Bye.